Alright. Hello. Hey, Clark. How's it going? Joey? Alright. General Canoe. It's a quality meme. It's a quality meme. Man, I fully planned on streaming Hearthstone this weekend, and then I found this new show on Netflix that I watched 8 episodes of, and so I didn't. But I might stream tonight now, assuming I get enough work done. Very close to hitting Legend again. Six people. How many people have actually turned this in? Seven. Right, and I know those two are traveling. It is kind of a fun game. I don't know. I enjoy it, but it gets stale after a while until new cards come out. They made a lot of changes that I have been against, but I think they're trying to improve things again. So it's not a bad time to come back. There's like a new expansion in 2 weeks. We lost viewers. That's not a good sign. Unless they were just random people, which is highly possible. My topology class has been getting like 9 to 10 viewers, even though we have 6 people in the class. So I don't really know who's watching, but it's kind of cool. All right, it is 11. All right, good. Number of people here is climbing. Okay, so I wanted to first just make a mention of the project, right? So I just want to see your project idea / one source, basically by midnight tonight. On Canvas, there's I think it's called just like project choice is the assignment. You can see the list of things under the big project where I give you all the details and like the kind of schedule of choice, outline, rough draft, and then final draft. Someone's getting a free education. So yeah, you can see that list. I give a little blurb on those things. If you're having any trouble deciding or you just want more information, just feel free to contact me. I can hang around a little after class in the Discord chat if you want to just discuss some ideas, or if you're having trouble finding sources, then I can help you with that. I did want to make one note here. We already have a quarter of the class doing cryptography, so no more cryptography. Anything else is fair game. There are several interesting projects on there, and I don't want to read all of them being the same thing. So if you're already doing cryptography, you're good, but yeah, no new choices can be cryptography. Okay. Any questions before we get started? I mean, today's assignment was pretty short, and I think we'll get through it pretty quickly, so I'm happy to answer any questions you have about stuff like coming in. If you feel uncomfortable with modular arithmetic and want to see something, yeah, I'm happy to talk about things before we get started. If you have any questions. From the ones I saw, I graded the ones that were turned in until like an hour ago, and they looked pretty good. It seemed like you guys had a pretty good grasp of this one, so uh, that's a good sign. Cool. In that case, I mean, we're going to end up proving some more challenging stuff today, which is why I didn't really assign it. I think a couple of these would be pretty hard if you didn't know exactly what you should be doing. So, yeah, let's get underway then. So U12, so this is 438. So we look for the guys that have GCD 1, right? So 1, 5, 7, and 11. Then we want to see our Cayley table, and seemed like everyone was getting this from what I looked at, but we can go through the process a little bit here just to make sure. So again, these are easy always. And then when you're looking at the other ones, right, you want to think, okay, like 5 squared is 25, and then 25 is 2 times 12 plus 1, right? 12 is your N here, and so 2 is like your Q, and this is your R, and so this guy is 1 in Z12 and also in U12 here. 7 squared, right? This is 49. This is 4 times 12 plus 1. And then 11 squared is 121, which is 10 times 12 plus 1. So all of these guys have remainder 1 here. And then you can just figure out the other guys, but you probably already know what group this is going to be, right? Because we only have 2 groups of order 4, and all of my elements are order 2 or fewer, considering the identity, and so this has got to be V4, right? But then what are the other ones? So 5 times 7 is 35, which is 2 times 12 plus 11, and this is abelian, right? Because we don't really, well, I mean, we're going to prove this in a little bit, but it's super fast. It's basically that 5 times 7 is 7 times 5, so they're going to have the same remainder as well. And then 11 times 7, 77, which is 6 times 12 plus 5, right? 72 plus 5. And so 7 times 11 here is 5, 5, and then 5 times 11. Well, you can either do it by elimination and say this has to be 7, or else our rows and columns thing won't work from, way back. Or you can actually just do it out and get 55 is, again, 4 times 12 plus 7. Okay. So that's our little modular arithmetic practice there. And so we've already kind of seen, here maybe I'll make a special notice of all of these guys square to the identity, right? They're all their own inverses. And so you can see immediately that U12 is not cyclic, right? You can get no more than 2 generated by any element. And it is, so all elements are their own inverses. And the order is bigger than 2, so can't have this. But it is isomorphic to V4, right? And you could show a direct isomorphism if you wanted, or again, you could cite the fact that we know there are 2 groups of order 4, right? We did that whole Cayley table proof. I don't remember what number it was, but basically we had like 2 options for how we could fill out the Cayley table, and you either get R4 or you get V4, right? And so since this is not cyclic, it's not R4, it has to be V4. Only 2 groups of order 4 up to isomorphism. Okay. And then last is the subgroup lattice, and this is another way to really see that this is a lot like V4, right? Is we have our 3 different order 2 subgroups generated by our 3 non-trivial elements. And then all of those contain, of course, the identity, or the trivial subgroup. All right. Okay. So 439, like, why is this abelian? Always. Abelian for all n. The main reason, right, is just multiplication is a commutative thing, right? These are still integers being multiplied. You just take the remainder after, but, right, so since AB is equal to BA, AB mod n is equal to BA mod n. Right, just because these guys are equal, so they'll have the same remainder when you divide, and so that's really just a one-liner. Okay. And it's the same for addition, right? So like Zn is always abelian as well, for the same reason. Right, because A plus B equals B plus A, so they have the same remainders too. All right, and then the next two were not too bad, I hope, but I saw some people doing more work than they needed to. So this one is for n greater than or equal to 3, Zn is isomorphic to Rn, Z2 is isomorphic to S2, and then Z1, which is just this guy, is isomorphic to the trivial group. So there's a long way and a short way here. So the long way is construct an actual isomorphism, right? You could do something like phi of n, phi of k, since we have n is fixed there. Phi of k equals r to the k, and then go ahead and show that it's one-to-one onto and satisfies the homomorphic property. Is there a faster way? Can you do less work? I know a couple people use this. Any ideas? Right. 427. Good. Yeah. I mean, yeah, the slow way is fine. So the lattice, okay. So there's a lot here. So maybe first, I want to address that one because this is toward the end of chapter 3. Let me see what number that was. 366. That's dangerous. So, same lattice does not necessarily imply isomorphic. So the other way is true. So this way, yes, but it doesn't go in the reverse. The issue there, right, is that you can have, I think we did the example of cyclic groups, right? So like R4 had the thing generated by R squared, this, and then R9 looks the same, right? It has exactly one subgroup in between, and so these have essentially, it's just renaming, but these have the same lattices, but they're definitely not isomorphic. They're not even the same order, right? So you have to be careful with that. So yeah, the quick way here is 427, right? So Zn is cyclic. What's it generated by? Yeah, it's just generated by 1. And often it's generated by other things too, right? It's in fact generated by k if GCD of k and n is 1. But we'll actually be proving that here in a little bit. How can you see the stream? It's always at this place. Okay, so it's cyclic, and therefore 427, right, says if G is cyclic of order n, then G is isomorphic to, again, it's basically the same thing, right? Rn if n is greater than or equal to 3, S2 if n is 2, and the trivial group if n is 1. Well, Zn is cyclic of order n. So we're done by 427. So that's the fast way. Right, just leverage the fact that you've done this work before, right? Because if you did it the long way, you probably noticed this sounds pretty darn familiar. Sorry, I'm gonna mute you, man. This sounds pretty darn familiar. Like I've proved this basically exact isomorphism. I did the 1-to-1 and onto in like exactly the same way. I feel like I should be able to use that previous proof. Well, yeah, you can. And so that's right. Once you notice you're doing like very similar work, you should think, can I cite something I have done previously? All right, so that's a good thing to keep in mind. Okay, so then 441, sorry, that was 440. 441 is G is cyclic. Then G is isomorphic to Z if G is infinite. And if G is finite, say order n, then G is isomorphic to Zn. Okay, so maybe I'll make these two different parts, right? So one of these is immediate from the previous, right? 2 follows from 440. And I guess 427, right? It's basically, we know that Zn is cyclic of order n, it's isomorphic to Rn, and Rn is isomorphic to any cyclic group of order n. So that's done. How do we get G is isomorphic to Z if G is infinite? Have we done this before? Do we have to show an isomorphism? Thoughts? Prayers? Have you shown anything about infinite cyclic groups being isomorphic to Z? I feel like we have. We use that there's no such in. Yeah, so I mean, you could do that, but that basically does boil down to, yeah, so we would want 429. So the statement of 429 is exactly if G is an infinite cyclic group, then G is isomorphic to Z. So this is actually just like verbatim what we want here. So be lazy, right? Don't redo work you've already done, is the moral of this problem. So yeah, 429 is exactly this. And so we're basically done. There's like actually no work to do in that problem once you've done previous things. Okay. Indeed. Bible thumb. All right. So let's do 443 first, and then I can talk about 442, and I'll kind of give you an idea of how I'll try to develop some intuition before we actually prove this. Um, but let's get a little list. So I don't know, shout out some things. I saw a lot of different things. So 443, what are some examples of G not cyclic, but with all proper subgroups cyclic? I saw a lot of different things. So yeah, yeah, that would work. V4, L8, and in fact, right, L2, L3, L anything would work. I know I saw at least one other one. From people. Yep, Q8 works. Right, its subgroups are like the things generated by I, J, and K are all cyclic of order 4. -1 and 1 is cyclic of order 2. Yeah. Yep. Are there any other ones? I think we're missing one big one that we've dealt with a lot. Yeah, S3, yes. Slash D3, right? Those are the same thing. Yeah, Jose, you're right. That was kind of what I was going for. So S3 specifically works. Sn in general will not work. So once you hit S4, you will have non-cyclic subgroups, namely the alternating group, which we'll actually talk about at the end of this chapter. Yeah, so Sn for n greater than 3, it does not satisfy this. Dn for n greater than or equal to 3 does. Right? Because, like, what are our subgroups? We've kind of seen this, right? So for Dn, we definitely have R, right, which is cyclic. That's order n. And then we have S, but we have more than just S. We actually have all things of the form, choose whether you want your R or your S to come first. But it's like R to the IS, where I is between 0 and n minus 1. Essentially, right, you have your n gone. I'll just draw a hexagon for kicks, right? All of these are basically like rotate and then reflect. So it's basically doing all of these different things. And so these are like the only subgroups we actually get. Our subgroup lattice is always like this big guy of order, half of the group, and then a bunch of things of order 2, right? Your one rotation group, and then all of your little reflection groups. And you have n different reflections, one for each vertex of your thing. Okay, so yeah, we've got a lot of examples, so that's good. Okay, so basically, it's the converse of 442 is like very much not true then, right? So just because you have cyclic subgroups definitely does not mean that you are cyclic yourself, and we have tons of examples. So this very much goes one direction. All right, so before we get into 442, are there any questions? All right. 14 people. Interesting. Who's getting the free education? All right. So let's think about this. So we know Z is cyclic, right? So I want to get your opinion on a couple of these examples here. So I want you to think like what are right, so the claim here is that any subgroup of a cyclic group is cyclic. So if I show you something that looks not cyclic, right, so I give you more than 2 generators, I want you to tell me what is the thing that will generate this group or subgroup. So let's look at like 4 and 6, 5 and 12, 15 and 105. And then let's do 30 and no, it's actually, let's do 30 and 75. So I want you to find out what cyclically generates these. So we'll call this A, B, C, D. So if you figure one out, throw out a guess, or, well, I guess hopefully it wouldn't be a guess. All evens for the first one. Yeah, I agree. A is equal to subgroup generated by 2. Right, because you can't get an odd from some combination of 4 and some combination of 6, but you can get 2, and thus once you get 2, you can get every even. B7. Is everything in there? So if you say 7, right, this would give you only multiples of 7. So you'd have like stuff, negative 14, negative 7, 0, 7, 14, and stuff. So this actually would not include 5 and 12. Yeah, B is actually generated by 1. This is actually Z itself. Delmas, how'd you get that? Clark, 5 or 15. So those are different. It is one of those. Which one is it out of 5 or 15? You're definitely right that one of those is true. Yeah, it is going to be 15. We can talk about why in a second. Yeah, okay. So, yeah, it's 15, right? Because you cannot get, basically both of them are multiples of 15, and there's no way to get 5, right? If you add, subtract, do some combination of them, you always get a multiple of 15. 5 is not a multiple of 15. Right. So A, basically, we can get 2 is equal to 6 times 1 plus 4 times negative 1 to get all evens. B, yeah, 5 times 5 plus 12 times negative 2 is 1. So once we have 1, we can get everything. C, 15 and 105 are both multiples of 15. This is like 424, right? This is basically 424, where, remember, we had that G1 down to Gn, x is equal to G1 down to Gn if x is in there. Well, this is the case where you just have like G1, right? Because 105 is in the subgroup generated by 15, right? 105 is 7 times 15. And so that would be your X in that case, and then G1 would be 15. So, okay. And then what about this last one? What about 30 and 75? Any ideas? Yeah, it's also 15. So why? What's going on with all of these? How are we finding these? Are you noticing a pattern? There's a nice little buzzword here, or maybe a buzz acronym. Yeah, exactly. The pattern is we're using math. I mean, I can't really disagree with that statement. Yeah, GCD. Uh-oh. Oh, there we go. Yes. So finding the GCD, right? So if you look at 30 and 75, the way I always think about finding GCD is I do prime factorization. So 30 is 2 times 3 times 5. 75 is 3 times 5 times 5. 3 times 5 squared. And so your GCD is like what they share in common, right? So they each have a 3 and they each have 1 5. So the GCD of 30 and 75 is 3 times 5, which is 15. I think that's, at least for me, if I have bigger numbers, that's the easiest way for me to deal with that. But yes, all of these are generated by the GCD. So my claim here is that this can be generalized. So if G is cyclic, and say it's generated by little g, and H is a subgroup of G, then H is generated by something. So I get, maybe I'll just say then H is cyclic. How do I find out what generates it? It seems like it has something to do with the GCD maybe, right? Because again, we said all cyclic groups are basically like Z if they're infinite, and then you can imagine that if you're in Zn instead, well, you still have the notion of a GCD. It's just that like you're restricting to just this finite set of numbers, right? So think about H. H is a subgroup, right? So since H is a subgroup of the thing generated by little g, this means any element in this subgroup is still some power of g, right? It's just that we don't necessarily get all powers of g. If H is in H, then H equals g to the k for some k and z, right? So we still got some collection of powers of g. So think about the positive powers, right? Because we know we get inverses for free once we're talking about a generating set. Then my claim here is that H is generated by g to the d, where d is equal to the GCD of all the powers, or you could even say like the minimum. I'll even do that, and I mean it happens to be the GCD. We can just do GCD. It doesn't freaking matter. All right, where d is the GCD of all positive powers. So g to the k, where k is greater than 0, and g to the k is an h. Had to think about how to write that there. Oh, sorry. GCD of k. Doesn't make sense to take GCD of things that are not numbers. Yeah. So basically, d is the GCD of all positive numbers k such that g to the k is in H. So this is a claim, right? I haven't proved anything at all yet, but does this statement make sense? So this is really just derived from our intuition based on looking at those little examples inside Z. But does what I've written make sense? Okay, cool. So let's prove it. So as you might surmise, we're going to be using the division algorithm, right? Seems to be the only way we can really do things. And so the idea is we're going to break down some. Can I explain the last line? This is just me reiterating in words like what I have written here. So basically, right, I have a whole bunch of things. The idea would be, right, so think about that 30 and 75. If you view G as 1 as your generator, right, then you could think of this as like G to the 30th and G to the 75th. And so if you look at all of the powers in H, right, you get a whole bunch of stuff, right? And so you end up with some collection of positive powers, and you can actually get G to the 15th is in H, right? So if H is generated by these two guys, because this is G to the 30th squared times G to the 75th inverse. I'm an idiot. This is the -2. This is a +1. Because 75 minus 60 is 15. And so basically my claim, right, is like 15 is the GCD of these two guys. And in general, if I took all of the positive powers, basically I can't get less than 15. I can only get things bigger, and they're all going to be multiples of 15. And so this is the guy I claim as my generator, right? Because you have a list of like G to the 15th, G to the 30th, G to the 75th, G to the 60th, G to the 150th, and a whole bunch of things. And basically all of these numbers, you take the GCD of them. Okay, so proof. Okay, so let's do it. All right, so basically the claim is H is generated by this G to the D, right? And so what does that mean? That means maybe I'll want, or my goal, if I take some arbitrary element of H, which we know has to be a power of little g, then we must show G to the K is G to the D to the something for some integer L. Right, that is what it would mean to be in the subgroup generated by G to the D. So this is our goal. And so let's go ahead and try, right? So we take a general G to the K in H, and then we can rewrite it as G to the, well, in this case, what are we dividing by, right? We're dividing by D. This is our common divisor. And so we are looking at, G to the DQ. We should be careful that these are not all necessarily positive powers, so I am just going to do the division algorithm in general here. So it's like DQ plus R, where R is between 0 and D minus 1. Okay. All right, now going to split this up. Okay, so what are we trying to show here? Basically, what I'm going to try to do is get the fact that this guy lies in H. So I'm going to show g to the r is in H, in which case, right, r is non-negative. So since r is greater than or equal to 0, then either r is 0 or d divides r, right? Because d is the GCD of all of the positive powers that lie in H. And if g to the r is in H, then r is one of those positive powers there. But this is impossible, right? Because r is less than d. So how can d divide it? So basically this would ensure that r is actually equal to 0. And then in that case, we get what we want, right? Because then g to the k is g to the d to some power. Okay, so this is the process here. So my next goal is to show that this guy actually lies in H. Okay. So, okay. So note that we know g to the k is in H. We're given that. And g to the d is in H by definition of d. By definition of d. Right, it is the GCD of all these positive powers. So like it is in H. We have defined it to be in H. Okay. Now H is a subgroup. Can you tell me why this is in H? So my claim now is we also know g to the dq is in H. Why? How does this follow from what we have previously written? And it's really just the g to the d being in H, not g to the k. So if you know g to the d is in H, why must g to the dq be in H? G to the d is not necessarily the identity. So yeah, this could be an infinite order group, for instance, right? Like 15 in Z. So we don't know that. Yeah, dq is a multiple of d, right? So this is g to the d to the q. But then, no, so that's our claim though, right? This is what we need to prove. But this is important. It is g to the d to the q. But we don't yet know that H is generated by g to the d. We're trying to prove it. This is g to the d times g to the d q times. Why must that still be in H? H is a subgroup. What do we know about subgroups? Yes, closure. Is in H due to closure. Good. Okay. So now my claim is g to the dq inverse is in H too, since H has inverses, right? So why is this important? Well, now I can rewrite this, right? So g to the k is g to the dq, g to the r, and so g to the r is g to the dq inverse g to the k. This is in H, this is in H, H is closed, so g to the r is in H. Okay? And now we get exactly that contradiction, but I'll go through it a little more slowly here. I was just kind of trying to give you a reason why I was progressing in this way earlier. So since g to the r is in H, and r is between 0 and n minus 1, either r equals 0 or r is greater than 0 and thus d divides r. Right? These are two cases. If it's positive, then d is the GCD of all the positive powers of g that lie in H. So d would have to divide r. Or it just is 0. The latter can't be true, since r is less than, d minus 1, sorry, d minus 1. Since r is less than d, so d does not divide r. Thus, r equals 0, so g to the k is g to the d to the q, which lies in the subgroup generated by g to the d. And finally, we conclude that H is generated by this guy. So I think, like, in general, it requires a bit of intuition, and I think that the examples with Z helps in terms of figuring out that GCD is like what really matters here. But then to like think of this and to think to show that G to the R and H it's pretty tough. So that's why I went ahead and figured I should prove this one. But hopefully that makes sense. Any questions on that? All right. Seeing no objections, I will move on. Can you explain why the last part again? What do you mean? Like the ladder? Like this, starting here? So basically, right, like R is a remainder. So we know it's less than D because we divided by D. Since it's less than D, there's no way that D divides it, right? You can only divide things that you are smaller than. So that means that R can't be positive because then we would get a contradiction with this D divides R part. And thus, since that part's not true, well, then the other case must have been true. So R has to be 0. And since we have a 0 remainder, right, then we had up above that g to the k is g to the qd plus r. Well, if r is 0, then this just goes away. And so we get g to the q d, or g to the d to the q. Oh, don't worry about the grammar. I just didn't know exactly where you meant. It wasn't the grammar that got me. Okay, so we get a really quick corollary with 444, and this is something we talked about a very long time ago, right? That all the subgroups of Z are in for, for any n, really. Right, these are all the subgroups. They're all of this form. And we kind of figured that out. We were like trying to look at those a long time ago, but we didn't really have the tools to prove it yet, right? I mean, you could say like it seems like the GCD or something, but this is like the full justification for that. Okay. Okay, so I want to do one last thing then, and this will start getting at the order of elements inside a group, right? So here, if G is cyclic of order n, so this one is finite order, so it's not like Z, then for all m in Z, you may want to know, like, right, I know all of the elements look like some power of G, but like, what is the order of that? And the answer is n over the GCD of n and m. So this seems kind of weird, and I want to maybe do an example first. So let's just think like in Z6, right? Like, what is the order of the element 4? Well, 4 is basically like G, so here your n is 6, and m would be 4 here, because you'd think of the generator 1, right? And so this is like 1 to the 4th, but it's additive now, so it's 1 plus 1 plus 1 plus 1. And so this would be 6 over the GCD of 4 and 6. Well, that's going to be 2. And so this is order 3. And that checks out, right? Because we get 4 plus 4 is 8. So this is 2 in Z6. Plus 4 is 12. And so 12 is equal to 0 in Z6. And we're back to the identity. So this is kind of what's going on. So to actually prove this, so that's kind of an aside, you have to do two things, right? So we're going to use the fact that n over the GCD of n and m is the smallest power of g to the m, such that you get the identity. Smallest positive power. So you're really trying to prove two things. One, you want that g to the m to the n over GCD of n and m is equal to e, and two, that that's actually the smallest. Okay, so the first thing is actually pretty easy. So I'm just going to call g, the GCD, sorry, d again, because I hate writing it over and over. So g to the m to the n over d, you can just rearrange this. This is also g to the n to the m over d. And note that d divides m, so m over d is an integer. So this actually like makes sense. I'm not doing any like fractional powers here. Well, what's g to the n? This is e, because it's order n. And so I get e back. So that part's easy. So then the other part is not as easy. But basically what we'll show is if we'll do this next time, but I will show this. So basically what we want to do, right, is if g to the m to the k is e, then we want d divides k. All you really need is actually less than or equal to k, but we'll in fact show that it divides it, which would imply it, which implies d is less than or equal to k, right? This is what it would mean to be the smallest. So if some other power gets you to the identity, then this guy is actually going to be smaller. And so what you should think about is use the fact, so this is a hint for, I guess, the daily for Wednesday, use the fact that d divides m and d divides n to get this. To get this along with, I think it's 424. Let me check really fast. No, 425. Right, you know that g to the mk is e, so you also know that n divides mk. So basically, these are your three pieces. So if you can use these three things, you should be able to get that d divides k. Okay? So, all right, that's a good stopping point. I'll be around on the Discord voice chat if you want to talk about like project ideas or something, or anything from class, until, a little afternoon if you want to talk for a bit, and then I'll get lunch. But all right, we'll go ahead and end stream.